Hello, welcome to the second pre-recorded lecture for Math 155. Today we're going to be talking about vectors. So in the last lecture we talked about points in some space, whether that happens to be a plane or three-dimensional space or an n-dimensional space. But vectors are crucially different because they describe moving from one point to another. So they're describing some change, and that change requires both a magnitude and a direction. So to give a practical example of why you might care about this, if we were to look at this antigenic cartography on the right-hand side, we might be interested in, well, what's the distance between any of these two clusters? So say from this 1968 cluster to this 1972 cluster, what's that distance there? Well, the distance will tell you something, but without the direction, without them, we just have a magnitude, just a distance. And so that just describes any place on this circle here. But we would want to know not just what's the distance, say, between two strings, but what direction you're moving in, how these two things relate to each other. And so, for example, a vector describing some movement here might have the same magnitude as another one describing movement here, but they have different directions, since they're telling us something different. Okay, so we're going to talk about vectors, and then we're going to talk about vector algebra as well. So a scalar is any object that can be described by a single number. So your height, for example, is a scalar. Whereas a vector is an object that can be described by both a magnitude and, crucially, a direction. So we need these two pieces of information to describe a vector. So for example, scalars, I mentioned height. We could have things like speed as well, distance. These are all scalars. But if we have speed plus direction, then that would give us velocity, which is a vector. Force is also another example of a vector because it depends on how you're applying that force. It depends on what you're doing. So if you're pushing, say, down on a box, you would crush it, whereas if you're pushing left on a box, you would move it along. So it's not just the magnitude that you're applying the force, it's also the direction of the force that's really, really important. Vectors can also describe the change from one point in a space to another. So for example, you could talk about, say, all of your collection of grades could be described by a point in a space, and how those grades change over time could be described by another point in a space, and therefore a vector could be used to describe the change in your grades. So in terms of notation, if we're talking about some sort of scalar, we'll just use typically a lowercase letter, whether it's x, a, beta, whatever it happens to be. Whereas if we're talking about vectors, we tend to write them as lowercase letters, but with an arrow. So for example, vector u, vector v. You'll also see them written in bold. So that's typically in a textbook, they might be written in bold, whereas see, it's harder to write boldface when we're just writing by hand. So scalars tend to be lowercase letters, and vectors can be lowercase. So scalars, just lowercase letters, and vectors can be lowercase letters in bold or with arrows. We're going to use the arrow notation for vectors because that helps you to think about the fact that you're moving in some direction with a vector. Okay, so the first thing we're going to talk about is how do we combine vectors. So when we think about a vector in some space, what it's really doing is it's going from one point to another. So if we have some vector v joining points A and B, it could describe this change here from point A to point B, where A is our initial point, or sometimes referred to as anchor. And point B is our terminal or head. So terminal point or head. So we have some vector here going from some point A to some point B, and this is therefore our vector V. So if we want to add two different vectors together, well, it's very simple. All we need to do is use our existing knowledge of algebra and just apply it to the different components of our vector. So for example, if we want to say, if I tell you to move 5 steps northeast and then 2 steps west, then that would look something like this. So maybe you move 5 steps northeast, we got vector u, and then let's put it in a different color. Suppose then you move however many steps I said, say 4 steps west. Let's call it our vector v. Then our net movement is going to be given by this vector w. So what that means is that we can describe u plus v as being the vector that goes from the initial point of u, so this point down here, so the initial point of our vector u, and that goes to the terminal point of vector v. So if we describe these as being separate points, so if this was point A, this is point B, and this is point C, then we can say that our vector w is equal to u plus v, which is just the vector from A to C. Now, as with scalar addition, when we add two vectors together, it doesn't matter which order we add them in. So this should hopefully make sense if you are asked to move in one direction and then in another direction. It doesn't matter whether you switch the order of the directions, as long as you keep the magnitude of those two things the same. So just to illustrate that, if we imagine that we have two vectors, u and v, so suppose this is our u, and let's do another vector, v, and we want to know what's u plus v, well, we can do that by doing u followed by v, so this is our u, and this is our v. Then u plus v will look like this, our w. But alternatively, we could have done v first, and then followed it by u, and we would have ended up at exactly the same point. So our w, which is our u plus v, it doesn't matter whether we do u plus v or v plus u, we end up at the same point. Okay, so that's how we add two vectors together. How do we deal with scalar multiplication now? So suppose c is some scalar and u is a vector, then the vector v, which is c times by u, is going to be the vector whose length is the absolute value of c times the length of u. With the same direction if c is greater than 0, and in the opposite direction if c is less than 0. And then if c is equal to 0 or if u is equal to 0, then v, our vector, is also going to be equal to 0. So what does this mean? Suppose we've got some vector u that looks like this. Well, what if our c is equal to 4/3? Then our new vector, let's call it v, is going to be pointing in the same direction as u, but it's going to be 4/3. It's going to be slightly longer. So look like this. And if we had a case where, say, our vector u looked like this, and c was less than 0, suppose it was -1/2, then our new vector v is going to look like this. So v here is going to -1/2 of u. So it's half the length and it's pointing in the opposite direction. So that's all hopefully fairly straightforward. Now, up until now, we've been talking about manipulating vectors geometrically, and this is a good way to start by thinking about what it means when we're adding vectors together, or when we're stretching them or shrinking them, or depending on what scalars we're multiplying them by. But when we're in many more dimensions, for example, when we have 79 dimensions describing the antisera for influenza that we discussed at the start of the lecture, we can't use the same sort of geometric thinking. So it's best to understand things algebraically, and we can describe exactly the same processes algebraically, okay? And we can do that by thinking about the components that form our vectors. So if, for example, we have some point in a space, AB, and this here can be described by a vector. So suppose this was point B, capital B, and this was point A. If that's starting at the origin, then the point U, the vector U, which is vector from A to B, is just going to be equal to a vector with components A and B, little a and little b. So for the notation with points, it can be a little bit confusing, but points we use circular parentheses, rounded parentheses, and for vectors, we would typically write them in these triangular points. So we'd say call this xy, or sometimes with square parentheses. The same applies whether we're in 2 dimensions, 3 dimensions, or n dimensions. So we can, again, if we want to draw a point in 3-dimensional space, suppose we go along the x-axis, on the y-axis, along the z-axis, to some point here, x, y, z, then we can describe this by a vector here. And that vector there, we call that b, that vector is going to equal the vector of components x, y, and z. So writing vectors down in this component form is a nice way of being able to write down what's going on with our vectors. And to give a couple more examples, if we have, say, in 2 dimensions, a point at 1, 3, then the vector that starts at the origin and goes to point 1, 3 here, we call this IU, is going to have components 1, 3. So this is the point 1, 3. Note the difference in terms of brackets, and that this is going to be different to, say, point at 3, 1, which has a vector with components 3, 1. And note that this is for a case where our vectors are anchored at the origin. There's no reason that our vectors have to be anchored at the origin. So for example, what happens if we have a vector that looks like this? Well, if this is our vector, what are its components? Well, we can just move that vector anywhere we like, as long as we're keeping the direction and the magnitude the same. So if we translate that down to the origin, our vector u is now here and has components 2, 2. So if you want to work out what the components of a vector are, all you need to do is move it to the origin and then look at what the final point is. That'll tell you what the components are. What about if we have vectors between 2 points? So suppose we've got a point P and a point Q given by some coordinates in the space. So suppose, for example, we've got point P at 1, 2 here, and we've got point Q up here at 3, 4. And then there is some vector, I'll do it in a different color. There's some vector U describing change from P to Q. So how do we work this out? Well, as above, we could just translate this down to the origin to work out what the change was. So if we translate U to the origin, then we'll be able to see here that U is equal to 2, 2. Alternatively, we could have just done an algebraic calculation. So we could have said, okay, U is equal to the vector from P to Q. Well, that's going to be, in this case, component x2 minus x1. So in other words, taking the component of the terminal point and subtracting the component from the initial point, and then doing the same in the y direction. And if we apply this to this example over on this side, so x2 is going to be 3, x1 is going to be 1, and y2 is going to be 4, and y1 is going to be 2. Then we end up with 2, 2, which is what we had if we just translated this point to the origin, this vector to the origin, sorry. How about if we want to work out what the length or the magnitude of a vector is? How do we do that? Well, this is very similar to what we did previously with distance. We can just translate our vector to the origin and then work out what the distance from the origin is. So the magnitude of a vector, which we write as these vertical lines either side of our vector, if it's a vector u with components u1, u2, then the magnitude or the length by Pythagoras is just going to be u1 squared plus u2 squared. We can see this if we go above. We can turn this into a right angled triangle, work out what the length of u is just by using Pythagoras. And if we're in more dimensions, same applies. So a 3-dimensional vector u with components u1, u2, and u3 has magnitude or length square root of u1 squared plus u2 squared plus u3 squared. Again, this applies in however many dimensions you have. So if we've got, for example, in 2 dimensions, if we had a vector of length, if we've got a vector with components 1 and minus 3, and we've got another vector, say, minus 1, 2, 4, well, the length or the magnitude of u is going to be the square root of 1 squared plus minus 3 squared, which is just going to be the square root of 10. And the magnitude of a vector v is going to equal square root of minus 1 squared plus 2 squared plus 4 squared. So 4 squared is 16, 2 squared is 4, and minus 1 squared is 1. So this can be square root of 21. So exactly what we've learned for working out the distance between 2 points, we can use to work out the length of a vector, because a vector is just describing the movement from one point to another. Okay, the final thing we're going to talk about today is vector algebra. So what do we do if we want to perform other algebraic operations? So if we want to add 2 vectors together, or multiply a vector by a scalar, or if we want to subtract one vector from another. Well, all we need to do here is we need to apply the same rules we use on scalars and apply it to the individual components within those vectors. So for example, if we have these 2 vectors u and v, which are composed of u1, u2 and v1, v2 respectively, in some scalar, so some c, which is a real number. then u plus v is just going to be equal to u1 plus v1 and u2 plus v2. So we're just adding the different components together, and we're doing that independently. If we've got some scalar times u, well, we just multiply the individual components, so c times u1, c times u2. And then if we do u minus v, well, this is going to be same as multiplying v by minus 1 and then adding them together. So we now have u1 minus v1 and u2 minus v2. So this is all very straightforward. For example, if we have, say, 2 minus 1, we're going to minus 3 times 2, 1. So we've got two vectors here, one of them being 2 minus 1 and the other one being 2, 1. And we're going to multiply the second one by 3 and subtract it from the first. Well, that's just going to give us, do it by component-wise, 2 minus 3 times 2, and minus 1 minus 3 times 1, which is going to give us minus 4 minus 4. So everything that you know about scalar algebra, everything you've done before you knew about vector algebra, you can apply those same principles of addition and scalar multiplication to vectors. Okay, that's it for today. Thanks very much for your attention.